going to have, as Bobby mentioned in the morning, we are going to have 4 lectures by the medalist. So this is the first one that we are going to have. Notice that on Wednesday afternoon, as you may have noticed from the program, there will be the ceremony in which you are all welcome to come, and the medalists are going to give another small lecture there. But so we will start today with Shinsei Ryu, who is going to talk about multi-wave functions, overlap, and applications. Thank you.
Thank you. So I hope the microphone is working. Yes. Okay. So yeah, thank you for this great opportunity. Today I'm going to talk about topics from many-body quantum physics and then quantum field theories. I'm a condensed matter physicist, and then the last lecture, when Kantaro asked, raise your hand, I didn't see many condensed matter physicists. So I feel like I'm the only experimentalist in the audience. But I think there's some common language we talk. So I guess, in fact, I got many inspirations from string theories to do my many-body physics research. And then I hope my talk will be also inspiring for the people in the other field. And in fact, some of the topics I'm going to talk about may be directly related to what Kantaro presented in the last lecture. Maybe he's going to talk more about in the next lecture as well. Okay, so let me start. So I'm going to talk about something I may call multi-wave function overlap. And I'm going to tell you what that is. And that's the, it shows up in various contexts. And then there are many applications. So the first application is about the application to the topology of many-body quantum physics. In particular, it is related to something called higher Berry phase. And then you may have heard about Berry phase, but not many of you may not have heard about higher Berry phase, so I will explain what that is. And then another application is the application in the entanglement structure of many-body quantum systems. So that is going to be the second half of my talk. And then there's a series of works, papers I have written with many collaborators. And then in particular for the topological part, the topics associated to higher Berry phase, I worked a lot with Shuhei Oyama. He's my main collaborator there. And then I also worked with the, okay, maybe I can use this. Bowe Liu, Junjia Dan, these are my student. And then again, Shuhei. And Yuya Kusuki is another long-term collaborator of mine. And, so together we wrote a paper on the application of multi-wave function overlap to study multipartite entanglement in quantum many-body systems. Okay, and then like the other lectures, please interrupt if you have questions. Okay, but let me start with the regular product or inner product, and then that's one of the most fundamental concepts in quantum mechanics. It's represent transition amplitude, and it also shows up when we compute the quantum mechanical expectation value. So it represents physically observable quantities. I'm going to use this type of drawing or diagram quite a lot. So in this simple picture, I have a, I don't know, one tensor with one leg, which is basically just to represent the quantum state. And then I have input. So the input one has the bond pointing up. But to make an inner product, I have also the output, which matches with this input. And connecting this, that means we are contracting indices. Okay? So that's the one of the basic objects. And I'm going to discuss the generalization of this type of object. Since I'm also making a connection with entanglement, it is also useful to think about the quantum mechanical inner product in terms of entanglement. And to see the connection with entanglement, I did draw this picture a little bit. So this is a picture representing quantum mechanical inner product. But we can sort of bend this bond and then bring this to up here. Okay, so then we get the next picture, this. And then instead of here, I have a bra and the cat. Sorry, maybe bra and the cat. But then I get the two bras, okay? But these two bras are connected by this bond now, okay? In equation, I can rewrite this inner product in this way using, here is a bra and the cat, but I'm now rewriting it using two bras. Wait, yeah, these are cats, right? Okay, I'm always confused with cats and bras. There's some sort of duality here, okay? But then the point is that then you have to put additional state here. In picture, this is a state sitting right here, and then this is the maximally entangled state, okay? So this is the connection with entanglement. So in a product, you can think of in terms of a maximally entangled state in this Hilbert space. And in this particular example, for example, a simpler case is that they have a two-dimensional Hilbert space of spin 1/2 degrees of freedom. In this case, you can put a Bell pair here. This omega is a Bell pair state. And then Bell pair state you can use to represent the inner product. And then in many-body quantum physics, you can have a more a complicated version of Bell state. For example, you have a thermophile double state, which can be defined in the many-body Hilbert space. And then once again, this it plays a role of connecting input and output, or bras and cats, and then it connects basically these two objects. Geometrically, you can think about these maximally entangled or entangled state as some sort of Einstein-Rosen bridge connecting different part of space-time. This is the famous slogan of ER and EPR. So the generalization I'm going to talk about today is to basically generalizing the Bell pair. I think there's many ways to phrase my generalization, but one way to think about it is, yeah, question?
Just to understand your picture.
Yeah.
So psi and phi are in the same Hilbert space, right?
Yes.
And in this picture, are they in the same Hilbert space or on the left and right?
This picture?
Yeah, when you connect it with the wormhole.
Yes.
So how should I look at this picture and relate it to this?
Yeah, so this is the two sides. I have two Hilbert spaces.
Two Hilbert spaces.
Yeah, left and right. And then...
so psi is in the left Hilbert space and phi is in the right.
Yes, exactly.
Okay.
Yes. Yeah, so I have two copies of Hilbert spaces. Yes. Thank you for the clarifying question. Other questions? Okay, so the idea is to generalize this construction to have many sides. Okay, here are the two sides. There's two Hilbert spaces. But I can think about generalizing it to have many copies of Hilbert spaces. So instead of considering in equation, instead of considering bipartite Bell state, I can consider a tripartite state, meaning I have three Hilbert spaces here with basis I, J, and K. And there I write down some entangled state. Although it's a bit delicate to talk about entanglement in multipartite setting, in the bipartite case, it's very explicit to discuss maximally entangled state and so on and so forth. But anyway, we are expecting that we may be able to generalize the previous consideration by replacing Bell pair in bipartite Hilbert space into more complex one like this one. In drawing, I have three Hilbert spaces, blue and yellow and purple. It's a tripartite Hilbert space, let's say. And there's some sort of correlations in this state. I'm just drawing wavy lines. Or in terms of geometrical thinking, we may consider the space-time with more than two sides. Here I have three sides, okay, and so on and so forth. And then then we come back to, we are kind of reversing the logic. Once we have a such tripartite state, we may be able to define a analog of inner product, but now for not just input out and output, but for more than two states. Okay, so that's the basic idea. So we can now feed states into these circles here, and then that may define something we may call a multi-wave function overlap, generalization of inner product. Questions? Yes.
So then what does the multi-inner product for more than 3 states mean?
Yeah. So three, I have 3 copies of Hilbert space, but I could have 4, 5, no problem. So I could have some sort of entangled state in n-party Hilbert space. But I can now feed n states into these. I can contract with n states on the left with this some sort of reference state V that defines a generalization of inner product. Okay? Yeah. So that's the generalization I want to discuss today. But I have to define it more, maybe not super rigorously, but more concretely. I will do that in various settings. So I studied this type of object in various topics, once again, in terms of topology of quantum many-body systems, and also in terms of quantum entanglement in many-body systems. As a specific settings, I studied 1 plus 1-dimensional critical spin chains. In terms of field theory, it's a conformal field theory in 2 dimensions. And then I also studied topological systems, gapped systems in 2D, and then, yeah, it's always a bit of a language barrier. So in condensed matter physicists, it's 1D and 2D. In high energy physicists, it may be 2D and 3D. But anyway, 1 plus 1D and 2 plus 1D. And then I think today I'm going to first focus on gapped state in 1 plus 1 dimensions. And then that's what Kantaro started to talk about in the last lecture. And I will use some of these languages, okay? Yeah, so let me say a few more things about this multi-wave function overlap. So in order to consider the type of generalization I'm speaking, it's really necessary to have a many-body quantum systems or kind of extended quantum systems, okay? So I just use a board. So regular quantum mechanics, I'm using just psi. And then if it is a regular quantum mechanics, there's really no internal structure here. I have a Hilbert space associated to some quantum mechanical system. I have a state psi, right? And then once again, in terms of picture, I have a, yeah, I can write it as a, in terms of some basis. And then this psi has only 1 index. So that's what I meant by this type of picture here, picture before. Okay, yeah, sometimes I put this on the top, sometimes on the down. But I think in the quantum field theory language, it's natural to think about this direction at a time. So I'm putting this way. But then there's only one bond I'm thinking here. And this bond can be contracted by another state, let's say phi, which may be ket, and then that can be contracted. But in this case, there's nothing I can do, okay? But in many-body quantum systems, let's say you have a state defined on a 1-dimensional space. For condensed matter systems, in many cases, I can think about a chain of spins, okay? And they interact with each other. Once again, I have some state psi to represent many-body quantum state, but in this case, it's a many-body quantum systems. And then many-body quantum systems has, well, it's still quantum mechanical system, but there's naturally the local Hilbert space associated to each site I. Okay? So then I have a expansion of my quantum state in terms of the local basis. So there's naturally this tensor product structure, psi, I, j, k, l, and so on and so forth. Okay, I think I have to write more cats perhaps, but anyway, I, j, and so on and so forth. Okay. So in terms of the drawing, it may be looking like this. So this is now a once again a psi. Here it's also the psi, but this one is only one index. Okay, because it's I just have only single Hilbert space. But once I have a many-body Hilbert space, I have a local tensor product structure. So it is natural to visualize such wave function in terms of this box, but now with many legs. I, j, k, and so on and so forth. So this is the like a higher rank, very higher rank tensor. Okay. So the idea is very simple now. So once again, coming back to this, there's only one way to contract. But now if I have a many, let's say more than two many-body wave function, let's say something like this, psi and now phi. This is another many-body wave function. And then there can be yet another wave function, maybe psi. So there are all some many-body ground state, or many-body, doesn't have to be ground state, but it's some many-body state. And then if it is just a regular inner product, I connect this bond to this bond to this bond, and then and so on and so forth. I just completely contract all these indices for every site. That defines the regular inner product between psi and phi. However, what I'm going to try to do today is to partially connect the part of this index in psi with the part of the index in phi. Okay, but I have the other part of the psi, and that can be contracted with another wave function psi. Okay, so now this can be contracted with this part. This can be contracted with this part, and so on and so forth. And then this part now can be contracted with the remaining part of psi. Okay, so essentially because of the local structure, I can naturally separate these indices into different set or different parties, and then these can be contracted separately. Okay, so I'm just saying in the many-body quantum systems, we may have more freedom than the regular inner product. I have a freedom to contract these indices, and then, well, at first sight, it just looks fun. We can have different kind of object. And then, but I want to try to demonstrate that this type of generalized version of inner product, which I may call multi-wave function overlap, they may be somehow useful in studying some properties of quantum many-body states, such as some topological aspect, and then entanglement aspect. Okay, any questions for this?
Just one quick question about this. So let's say in the usual notion of a scalar product, you cannot connect randomly. Like you really have a clear way of doing things that has to obey usually some positivity of sorts. So I was wondering, how does this notion of actually being a scalar product that generalizes to having more than two things appearing in your construction?
Yeah, that's a very good question. I don't think I can axiomatize this kind of multi-inner product, a higher inner product, as nicely as we do in the quantum mechanical systems. For example, we may want to have an invariance on the local unitary transformation. If you make a change of the basis for every site, we may require the invariance and such. So that can be, for example, naturally preserved as far as I contract each site. That is a notion we don't have in the, if I think of this as a one big quantum mechanical system, because then there's no way, no motivation to think about unitary transformation acting for each ijk separately. So yeah, that's just a natural kind of very simple, maybe too simple example for the one requirement, which is obviously satisfied. There may be many other things. Once again, I don't have a perhaps the very concrete answer. What I'm going to do is as follows, which may answer some of your questions. So I'm using this quantum mechanics or maybe tensor network languages. In many of my work, I will try to map or connect these objects to particular path integrals, okay? Sometimes I can, sometimes I cannot, but in many of these good quantities I'm looking at, they can be all mapped to some sort of path integral in quantum mechanics, either in conformal field theory or in topological quantum field theories. So my thinking is that as far as I can map these calculations to these path integrals, they are sort of very nice object because they satisfy kind of required properties by path integrals or quantum field theories.
Sorry, quick question. If I think of this three-fold inner product as a path integral, then is there any sense in which, for example, if I integrate over phi, this reduces to the usual inner product between psi and
yes, so very good point. So some of these can be naturally associated to partial trace. Not always. So in the application of related to entanglement, many of them, I think it's all of them, can be associated to reduced density matrix. After tracing out some region, then you contract. For the first example, higher vary connection, it's not always so.
Sorry, if I think in, okay, maybe this is too naive a picture, but if I think in conformal field theory and use a state operator correspondence, then you can relate the usual inner product to a two-point function.
Yes.
So is it really computing like a multi-point function?
Yeah. So in the yeah. So that's precisely what it is, and then it's also yeah. So I don't discuss this example, first example today, but in the first example, it is the it has an effect of extracting OP coefficient, for example. And then from CFT, specialists, that's perhaps not much. It's just that's what it is. People who are working on lattice quantum systems, multi-inner product provides a very convenient way to extract three-point function, OP coefficient, and some scalings associated to it. So it can be used as a numerical too. Yes. Okay, so let me move on. So, but once again, I want to specify very, yeah, so this is the basic idea. I think a basic idea is relatively simple. But I have to specify, well, it's good to specify which class of many-body state I work. So for example, it's true that generically I can write a many-body state in this way, just expansion in terms of some basis. But if I consider, for example, gapped topological systems in one dimensions, and then maybe in higher dimensions it's a bit more complicated, but in one dimensions, if I consider gapped quantum systems, it's a very good approximation to write this psi in terms of some building blocks. So we can write this big tensor psi in terms of these smaller tensors using, okay, I think Kantaro called it W, I may be using A. So this is called matrix product state. Okay, so this is the almost equal. I mean, it's not exactly equal, but it is enough to consider matrix product state if I'm interested in the class of state which are gapped in 1 + 1 dimensions. There's some perhaps a bit more conditions, but that's basically what I'm going to do. Okay. All right. So maybe one more thing is that for class of state, matrix product state, I'm going to study. Okay. I'm going to study this inner product for 3 states defined here. So I have a 1 state which is colored blue, and I have 2 other states, red and the blue, and then they are contracted with each other partially. So the part of this chain is contracted with the one part of this chain, but the other part is contracted to distant. Okay, so so this is the example of multi-wave function overlap. In this case, just the 3 parties, and then I'm going to study this object. In particular, this one turns out to be very useful to study something called higher vary phase. So let me now move on to just explaining what higher vary phase is.
So in HepTH language, when you consider these states for a gapped system, that's like saying that we only concentrate on the topological quantum field theory describing this? Okay.
Yes. So that's basically the same thing. So critical state CFT, gapped state, NPS, matrix product state. Or, sorry, gapped state TKFT. That's right. That's the translation. Okay.
I have perhaps a naive question about these diagrams that you're drawing. Is it always true that the lines start and end in a state and that they don't have something like a vertex? I mean, in the back of my mind.
Yeah, so we can insert, for example, defects. So this is the simplest thing that we could do a bit more, in fact. And then
in the back of my head, I'm thinking of something like, using this notation to write a Clebsch-Gordon coefficient. So would that be like 2 lines going in vertex and then?
Yes. Yeah, so that would be like, so it can show up, for example, so not in the simplest application I'm talking about. For example, the particular example I know is that you can consider the non-invertible symmetry acting on matrix product state, and then symmetry line, so symmetry is a line, but they can fuse. So that will be a defect or vertex. So that can happen. In my example today, it may not happen in 1 + 1D, but in 2 + 1D, we will see that. Questions? Okay, I hope it's simple enough. I mean, I use some language from matrix product state, but for today's talk, you don't need much of the knowledge on the matrix product state. So let me now explain higher vary phase, what that is. But before that, I just review regular vary phase, which is simple enough. Okay, so what is vary phase? So we consider a quantum mechanical state psi, but now it depends on the parameter. So parameter x it can have multi-component. I'm just writing it in this notation. And then the idea is that as you change x, this quantum state psi also changes because it's psi which depends on the x. And then you want to know how much the state changes as you change this parameter x smoothly. And then, so I'm thinking x is some part of parameter space, for example, sphere or some other manifold. So you have an ability to change x on M. It's like your experimental knob, okay? And then you observe how much the state change psi. And as it turns out, to first order in x, the change in the wave function psi is purely imaginary. So it's only the phase part of the wave function that changes as you change x smoothly. And then you can also keep track of then how much the phase, how much phase I accumulate as we as we make a loop in the parameter space. So that is a Berry phase associated with this loop gamma in the parameter space M. And then, as well known, it can be computed as follows. So first, so this is the first order change in x. I'm changing x as a function of time. And then the first order change in the wave function is this overlap between the initial state and the derivative of psi. And that is basically the first order phase. But I can integrate this first order change over this loop gamma. So that is a phase accumulated along the process. So that's the Berry phase. It can be represented as an integral of this object, A mu. So that is a one form on the parameter space. And then you can think about integrating this one form, which we call Berry connection, along the loop. So it is pretty much like a regular U1 gauge field. And then integrating this A along some loop is a Berry phase. Okay, I think this is very standard. Higher Berry phase. Oh yeah, maybe one more thing. So then I also want to talk about the topology. So I have as before, I have a state psi of x. So psi depends on parameter x. And I can think about this as a family of state, quantum state, parameterized by x. So I can, instead of consider single state psi, I'm now considering a family of state. Okay? But this family of state can be topologically non-trivial in the sense that if you compare two families, psi x or psi x prime, these are two families. Sometimes you can continuously change one family into another, but sometimes you cannot. Okay? It is well known that when it happens, there is the monopole in parameter space. Another way to say this is that you can define a topological invariant for each family, which is defined as follows. So you have a parameter space x, which now, instead of a loop, it can change over all parameter space. And then if you specify one family, you have a given configuration of the Berry connection. And then you can also compute the curvature associated to the connection, which is this f. Integrating of f over n turns out to be just integer. And then for a given family, you get a particular integer. And then the idea is that if you have two families, and then if you compute this integrals, and then if these two integers different, these two families are topologically distinct. Okay? So this integer is associated to the Dirac monopole in the parameter space. So this counts the number of, maybe in the picture, I have some parameter space, and which can be closed. It should be closed, but I'm just drawing this in like open surface. And then for a given quantum state, I have a configuration of the curvature, which I'm just drawing as a flux. Okay, and then when you integrate this curvature, it is integer in the unit of 2 pi times I. In that case, somewhere in the parameter space, not in the parameter space, but somewhere here, outside the parameter space, you have a monopole, which is sourcing this gauge field configuration. So this is the, let's say, one family. For a given family, you have such configuration. But if you have another family, in that case, you may not have monopole here. Okay, so no monopole. So these two distinctions can be detected by considering this integral. Okay, so I'm going to generalize this to many-body quantum systems, so that's why I'm mentioning it here. In particular, I'm going to generalize the something called Wu-Yan's approach to magnetic monopole. So let me also review it here. Okay, so how do I see the non-triviality of the quantum mechanical wave function? So in order to see that, we consider patching this parameter space. Let's say I have two patches here, U alpha and U beta, and I could have more, but let me just draw two, okay? And then the idea is that for a given patch, I can have a quantum mechanics wave function with a smooth gauge. So my wave function changes continuously on this patch U alpha. However, once I have a monopole inside, I may not be able to take smooth gauge choice for the total parameter space. So I may have to patch. Okay, but anyway, it's good to patch my wave function, anticipating that it may not be possible to define a wave function in a uniform way. Okay. So once we define a wave function using these patches, then we can now study what happens when these patches overlap. Let's say in the simplest case, I just take two patches, one patch for the north hemisphere, the other patch for the south hemisphere, and they intersect somewhere in the equator. And you can ask how much, so physically these wave functions represent the same state. They differ only by the phase, okay? So they differ by the phase, so I put some phase here. And then when there is the if there's a non-trivial monopole, or if the integral of this f is a non-trivial integer, there's a winding in this phase phi. So that is a way to characterize this integer, or that is how we see non-triviality of the family. Okay, so this is called Wu-Yan's construction, or Wu-Yan's approach to magnetic monopole. This is also fairly standard. Okay, so this phase appearing here, I may call it transition function, which relates wave function in two different patches, and then from that we can reconstruct the topological information of this family of states, or a complex line boundary in mathematical language. Okay, so this is two slides for the regular Very phase. I hope you may have heard about it. Perhaps I didn't explain in a very coherent way, but yep.
Little question in the before.
Yeah.
The before slide.
Yeah, previous slide.
Is only a phase, or is assumed in the index of the in beta, for example?
This phase
There is assumed in beta, or is only a phase?
This is only a phase.
Only a phase.
This is only a phase, because these two states are, so I'm looking at intersection, and I'm looking at the point on U alpha, point on U beta, but they are physically the same point.
Okay. Okay.
So physically the same state, so they can differ by the phase.
Okay.
Only by the phase.
Perfect. Thank you.
Hey. I have a question about notation. Maybe here by U1 with the dashed downside, do you mean locally constant value, the U1 function?
Yes.
Okay.
Yes.
Very good. So you are not allowing phi to depend on space, right? So the boundary is flat.
Yeah. So this is called I think it's called sheaf. I don't know much about it, but this is the notation. And then sorry, I didn't explain that part. But
No, that's good.
Thank you. Yeah. So maybe I should just want to say that this defines a second cohomology class in mathematics, and then different classes correspond. So each family belongs to a particular class, And then this class called Chan class is the topological invariant of this family. And then Chan number, this integer is a kind of way to distinguish these classes. So we are interested in which class we are having in my system. Any questions? Right. So the generalization I want to discuss today is this higher Berry phase, and then I think it may be known in various contexts, but in many body physics contexts, for example, there's a famous unpublished work of Kitaev, and then many people followed up on this. So I'm only listing some of these relevant, at least early works on this subject. But the idea is that I could have, instead of one form Berry connection, I could have something called higher Berry connection, which is now two form. Okay? So that is the generalization I'm talking about. Okay? And then if the connection is one form, curvature is two form. But if a connection is two form, I could have a curvature which is three form. So this is the type of generalization I'm talking about. And then I just first want to illustrate using some sort of analogy between particle quantum mechanics, regular quantum mechanics, and then the quantum mechanics of extended objects such as string. This is sort of some illustration, but I will, instead of using string in string theory, I will use this matrix product state, which is the extended quantum mechanical system. Okay, so, but let me see the sort of how this analogy works. Let me once again come back to this. So I have a particle trajectory in the parameter space, which is associated to the trajectory or loop. Yes, I can think of this loop as a trajectory of the particle in this parameter space, M. And then if I have a particle, the current of the particle can couple to this U1 gauge field, Berry connection, minimally. And in fact, you can rewrite this Berry phase in terms of the particle current. Okay, you draw the trajectory, define the particle trajectory, and then you define the current, and you can interpret this as a coupling between particle and the Berry gauge field, Berry connection, and then this can be at least formally generalized as follows. So instead of considering the parameter which changes as a function of time, single time, you can now think about the something which depends on two coordinates, t and sigma. Okay, and therefore associated to this xt sigma, there must be some associated state. Okay, the nature of this state I cannot discuss now. I will use a matrix product state to make it more concrete, but I have some state which depends smoothly in some sense on xt sigma. Okay, in that case we can consider a current associated to this extended object string. Okay, so this is the formal definition of string current, but string current is two form. Okay, and since it's a two form, it can couple to the two form gauge field. Okay. So in terms of picture, previously I had a particle trajectory, and then I have it's a one-dimensional object which couples to one form. But now if you have an extended object like a string, it can sort of sweep the part of the space-time, which may now looks like this membrane or part of the parameter space, which looks like a surface. And then for the surface, you can couple this surface to this two-form gauge field. Okay. So this is this is something we may expect as I generalize the Berry phase from a particle to some extended object. But what is a bit mysterious, or at least not obvious here, is that everything about classical part is completely understood this way. But I still have to discuss particular state psi, which depends on this classical entity, capital X, smoothly. And then this is a bit non-trivial thing to do. So I will use more concrete setting where I only focus on the gapped 1+1 dimensional quantum many-body systems. Okay, so I'm going to use this matrix product state. So I only consider a class of state which are represented by matrix product state. Okay, but now I can consider, but otherwise it's a very similar setting. I consider a family now which depends on some parameter x. And x, so this state psi depends on x because this matrix or tensors in the matrix product state depends smoothly on x. Okay, so this is the setting I want to consider. So I have a smooth one class of 1 plus 1D many-body state which depends smoothly on x. Okay, so once again the question is this: is there topological distinction between the families of 1 plus 1D state, 1 plus 1D gapped state? Technically, I also say invertible 1 plus 1D gapped state, but for now it's okay to just say gapped state. And then, is there such topological distinction? And if there's a topological distinction, what is a way to distinguish them? Is there topological invariant, such as the monopole? Okay, so that is the question that I'm asking. So what I do is to once again start patching this parameter space. Okay, so I have here. Let me start with 2 patches, U alpha and U beta. And for each patch, I have a smooth matrix product state. And then I can ask what happens at this intersection once again. Okay, so it's pretty much the same as before. So these 2 quantum states, they must be related to, they must represent the same quantum mechanical state, right? And then, so that's why the phase we talked about here. But now it's a bit more, we have a bit more resolution to discuss this question. So I have 2 matrix product states, but they must be physically the same, okay? So that is the condition imposed on the tensor on the patch alpha and tensor on the patch beta. And then more specifically, if they represent the same quantum mechanical state, these 2 tensors must be related by conjugation of this G up to some trivial phase. So the phase part is not very important for me, so, but it's there anyway. So pictorially, this tensor must be related to this tensor if they are sitting on the same point by this relation. And then the meaning of this condition is perhaps fairly intuitive. If I have 2 tensors, A and A prime, but now these 2 states must represent, 2 MPS, they must represent the same physical state. If A and A prime, or A alpha and A beta, if they are related by this way, which means A beta, I can write this way, E beta is essentially A, and I have G here. I think I'm using this gray box here, G here. And they have a G dagger. But this A prime here is also G dagger. It's sandwiched by G dagger, and so on and so forth. So the one tensor coming from the left and the other tensor coming from the right, they just cancel with each other. So they obviously represent the same physical state. So if I have 2 MPS and representing the same state at this intersection, they must be related this way. Okay? But to see something interesting, we have to go up to the triple intersection now. Okay, so now at the triple intersection, I have 3 matrix product state. Let's say one from the patch alpha, the other from beta, and the another one from gamma. They are sitting, so I have a triple intersection. I can consider the one point in M, which belongs to all these patches. So if I do it in the quantum mechanics setting first, then we get something called the co-cycle condition, which is perhaps not so difficult. So now I have a phase or transition function associated to U alpha and beta. So I have E I phi alpha beta. And similarly, I have another transition function from between beta and gamma and alpha. But now to go from psi u alpha or psi alpha to psi gamma, I can consider two different ways of relating these two wave functions. So psi alpha must be related to psi in gamma patch by this phase, by definition. But I could do this by first relating psi alpha to psi beta, and then psi gamma. In this case, I accumulate two phases, phi alpha beta and psi beta gamma, but this must match with phi alpha gamma. Okay, so this is kind of condition we get. This condition we get. So this is a regular quantum mechanical setting. And then next thing is a non-trivial step. So I could do this now with a matrix product state representations. So with matrix product state representations, I could relate the matrix product state in the patch alpha and then the another matrix product state in patch gamma by two different ways. So first, I relate matrix product state in alpha and gamma by the condition we just discussed here. Okay, so A alpha and A gamma, they must be just related by the conjugation up to some phase. Okay, this is something we discussed at the double intersection. But now I can relate A alpha and then A gamma by first relating A alpha and E beta. They are related by conjugation. But I can use this relation once more to relate E beta and E gamma, and they have to agree. Okay? So that imposes the condition, this condition where G alpha beta G beta gamma times G alpha beta must be related like this up to some U1 phase. And then this is the analog of exponential I phi alpha beta, the phase associated to the double intersection, but for the MPS, or for the extended quantum many-body system, we get the phase associated to the triple intersection G alpha beta gamma. So that is the analog of E2 I phi alpha beta, but now it has more index, and it is a many-body quantum physics analog of this. So this is the related to the higher Berry phase. I'm not using the two-form differential form notation, but this is the analogous to the Wu-Yan's description of monopole, but in a higher version of it. So that's kind of the first highlight of my talk today. And then I wonder if I'm losing you because I'm using a bit of a matrix product state language.
Just to clarify, what you're calling ambiguity of ambiguity is the zero-form gauge invariance of the one-form gauge parameter?
So G alpha beta is already ambiguity relating to matrix state. But here I have a U1 phase ambiguity in some sense, because these two they don't have to agree. They only agree up to this ambiguity. So it's like ambiguity of.
Yeah, I'm just trying to see that from the gauge fields you wrote down. So you're just saying that B is invariant under B plus DA, and then the A itself has an ambiguity because A is invariant under A going to A plus D gamma?
Yeah, in the differential form, yeah, that's perhaps, yeah, that's the way to say it, yeah. I may prefer to say it this way, but yeah, that's morally correct, I think, yeah. Okay, so in the previous case, the quantum mechanics case, this is a way to see the non-triviality of the family, and that is associated to the second cohomology group, or Chang class of the manifold parameter space M. And here it is now associated to the third cohomology class. It's called Dixon-Doherty class. So that's the topological invariant for the family of parameterized family of matrix product state, or 1 plus 1 degapped state. That's a topological invariant. Okay. Then I could say a bit more maybe application. What does this mean physically? I don't have a preparation for this, but for the family of regular case, for the family of state distinguished by the Chan class, it is a topological invariant associated to the family, but you can also think of this as the topological invariant associated to the process, because as you change T, you have a family of state parameterized by let's say some parameter time, so you can make a loop. And in this case, it is related to something called Soudess pumping in condensed matter physics. That is the topological phenomena associated to the adiabatic process. And there are similar, slightly more interesting adiabatic, the phenomena associated to this third cohomology class, or Diximier-Duadie class. So yeah, okay, I'm sorry that my explanation here is a bit too maybe condensed matter physics oriented, but in order to make things precise, I want to proceed this way, but nevertheless, now I want to make some connection with quantum field theories and also string theories, okay? Oh yeah, maybe I haven't, maybe I haven't said, actually, sorry.
Question.
Yeah.
Yeah, I was about to ask this question. I think you're going to answer it now.
That's right. So I said this is the highlight. The previous one is actually not the highlight because I have to explain what we did in terms of wave function overlap. That is the highlight. Okay. So highlight is that this Diximier-Duadie class, or the set of these phases, it can be extracted by considering the multi-wave function overlap. That is perhaps sounds natural by now because double intersection, you can consider the regular wave function overlap like Wu and Yan did. And then, but now we can generalize this to triple intersections. I have a 3-matrix product state, and I want to extract this phase associated to it. To do that, we can consider this multi-wave function overlap for 3-matrix product state. And then in this notation, regular inner product would be just 2 lines contracted or connected by this vertical bond, but I have a 3-matrix product state and connected with each other in this form. And then we can show that this does actually extract this Diximier-Duadie class C alpha beta. And then technically, I want to do it in the thermodynamic limit such that the number of vertical legs here and the number of vertical legs here, they become infinite. So there's some technicalities I may have to explain here, but you can believe me that I can do this calculation in the thermodynamic limit where the number of these legs becomes infinity, and you can check that it will extract this phase C alpha beta gamma. Okay. I think I may need a bit more background to explain these technologies, but I think for the purpose of making this talk simple, I just state that this can be calculated in a thermodynamic limit. Okay? So this is a fairly standard calculus in the matrix product state. Okay, so now I really want to the part here which connects with string theory. So I'm not an expert, so I really appreciate an input from you, but I think what I'm having here is very similar to string field theory, or maybe even equivalent. Okay, so I'm inspired by this work by Edward Witten, which is a famous paper on the open string field theories. So I'm using matrix product state, but I also introduced this concept using the analogy between particle and string. And then I looked at some of the string theory literature, and then this came up. So in this paper, describes the string field theory vertex, which describes the interaction between strings. And then this is the picture which he drew in this paper, which is almost exactly the same as the picture I drew. Okay. So I think it's really the same thing. Although I'm focusing on since I'm focusing on the topological state, gapped invertible state, here it's maybe just conformal field theories, but otherwise it's very similar. Just to explain what is written here in this paper, I have here the interpretation in my language. I think it's perhaps really the same thing. So I can define something called this star product in string field theory. And then, once again, you can look at the definition of a star product in string field theory. But here I use the matrix product state way of defining it, and I think it's really the same. So what do I do here? So I start with the one matrix product state, and I'm kind of suppressing boxes to make the notation simple, but this is my way of drawing matrix product state. I have many legs. These represent physical degree of freedom, but I have also the vertical line. Okay? I can first consider a multiplication of two matrix product state. In order to do this, I split my index first bipartition my matrix product state at the middle, and then I split the indices into the left, and then the set of indices on the right. I have a two set of indices now. Similar thing I could do here. So I first contract index here to the index here, and then I kind of bend this string or MPS. So this part and this part, they are left uncontracted, but they are now contracted, okay? Using the matrix product state calculus, you can actually, there's infinitely many index here, but using the calculus of matrix product state, you can sort of remove this part. You can safely remove this part. So essentially, it defines a kind of string, which is now a mixed in the sense that I have a state alpha on the left side and state beta on the right side. Okay? So this is the star product. Only thing I'm saying here is as follows. So you can think about this matrix product state as a big matrix, thinking the left part as the input or maybe output index, and the right part as an input index. So you can just view this as a big matrix, okay? And then multiply. You can also consider something called integral here. And the integral in this context is that you bend this NPS in the middle, and I flip this part over and then contract. So that defines this bubble type diagram. So it's just computing the inner product of the norm of this state. And then finally, combining all these ingredients. By the way, yeah, so this is really the same as what is written here. I'm just translating this using the kind of discrete language. Now you can consider the product of three matrix product state, and then you can do the integral here. And following this rule, this is nothing but this triple inner product. Okay, so if I'm not mistaken, I think this string field theory is really computing higher Berry phase. Okay, or outcome of the string field theory may be considered as a higher Berry phase. Okay. So far we just discussed the generalized version of Wu Yan's perspective to higher Berry phase, but we can also discuss something like a higher Berry connection, two-form connection, and then three-form curvature. There's a very recent work on this topic, but I think I have to skip this. But I'm happy to take, yeah, please ask me if you are interested. Questions? Yes.
In a string field theory action, the kinetic term has a QBRST. What is QBRST in your description?
That's a very good question. So I don't have a G2 grading. I try to identify something called G2 grading. I think in string field theory context, it's a BRST operator. If I have that structure, I can fully perhaps promote this MPS structure into the, I don't know, non-commutative geometry. Since I don't have this, I don't know what is the BRST operator in matrix product set context. I can't say this defines non-commutative geometry, but if I have that one, this is fully-fledged non-commutative geometry. So I'm very happy you asked, but if you have any ideas, please let me know. Yeah, so that is a missing element.
Thank you.
Yeah, so the string field theory vertex looks a bit like fusion of sectors. So does your C alpha beta gamma sort of can be viewed as, it's not literally a fusion coefficient because it's a phase. And also it's not, at least in your setting, it doesn't seem to be natural to be summing over a gamma or to multiply by summing over an index, because you're basically just looking at an overlap of three patches. And so something like associativity or so of the C alpha beta gamma is that a requirement? Or?
Yeah, so I have a few things to say about this, so I'm very happy you asked. So I'm going to use similar thing in one higher dimensions. In that case, as it turns out, if I discuss multi-inner product in one higher dimensions, conformal field theories start to appear because of the bulk boundary correspondence. And the certain calculation, in fact, can be phrased in terms of the F symbols. And from that perspective, we can say higher Berry phase is the ambiguity, phase ambiguity of the F symbol. So that is the connection. So in this dimension, although I'm a bit confused, so we can perhaps chat about it, but there's clearly such connection. Then the other thing I want to say, maybe I just forgot, so I can tell you later. Okay, are there other questions? Okay, so I think I'm halfway through, and I think time is almost up, I guess, but it's not too bad. I think this is the main part. So I just want to quickly mention this kind of thinking can be generalized in many ways. So it can be, first of all, can be generalized to higher dimensions, okay? So we go from strings to membranes, and then it gets more difficult and complicated because tensor networks in higher dimensions are, I think, less understood. But we can certainly discuss this generalization. For example, in 2+1 dimensions, I can consider gapped state in 2+1 dimensions, and I have to specify what kind of, which class of states. But for example, I can consider invertible. I'm not sure I've introduced this terminology, but there's class of very simple gapped state in 2+1 dimensions. And then I can consider a tripartitioning such state. So in 1+1D, I had a bipartition. Okay, and I had the 4 state. In high dimensions, I could consider tripartition of the plane. This looks like a disk, but you should think of this as an infinite plane. And I can tripartition the plane, and I can get 4 state, and then I can start connecting these 4 states. And in the picture, it looks like this. I'm not sure if you can see it, but I have one facet here, and in this membrane, I have a region A, B, C, and for example, A is contracted with other face, part of the other facet, and so forth. So obviously, it's more difficult to draw. Nice way to draw is to just use more compact notation. I just write psi in terms of this ijk basis. I just represent a set of state in region A. J represents set of state in region B, and so on and so forth. And then if I connect these contract, I can draw some diagram which represent how these indices are connected. Okay? In this compact notation, the triple inner product looks like this. I have a state psi, which is bipartite. So bipartition, so that's like 2 legs, and one of the legs is contracted to the leg of one leg of psi beta, and so on and so forth. In one higher dimensions, I have a more complicated network, but still we can discuss. Then other generalization is to quantum entanglement. So in addition to discuss the topology, we could also discuss entanglement in many-body quantum systems. Since I'm multi-partitioning my many-body states, we are basically discussing multi-partite entanglement. Okay, so for example, even for the single spin, not single spin, but even for the quantum mechanical spins, I could have an interesting tripartite state, which are not like a Bell state, but this is the entangled state specific to three parties. There's something called GHZ state and the W state, and then we can use quantum entanglement to distinguish this multipartite state. In the many-modi setting, it's a bit more complicated, but nevertheless, we want to discuss what is the multipartite entanglement structure in D dimensions. So let me mention at least one quantity, and then perhaps I have to end. So that is something called multi-entropy, and then using this notation I'm introducing, it is written this way. So there are some equations, but it's perhaps better to just understand in terms of drawing. So I have my state, but it now have a tripartitioning. So that means I have three legs coming out. One is associated to in the region B, A, B, C. So this is just writing psi ij k using this box notation, tensor network notation. I can first consider reduced density matrix by considering the copy of this. This is actually a bra, so I may put star here. So A, B, C. But I can first partial trace region A. So that means I connect these two bonds. So this is rho BC. So connecting means I'm tracing over degrees of freedom in region A. So this is the way of writing the reduced density matrix in this notation. Okay. Now I can consider 4 copies of this. So I may have something like this for 1 copy. But I take another one here. Once again, region A is traced out, so this leg is connected. But I have let's say BC, BC, BC. And then I can connect B and C here. Okay, so this is what is happening here in this diagram. So this part represents a one reduced density matrix. This is the region A, which is traced out. I have another one here, which is another reduced density matrix associated to region B and C, but I contract this index here. But index associated to region C is connected to yet another reduced density matrix. So you see 4 vertical lines, like 4 vertical structures. Each represent a reduced density matrix, and it's contracted this way. Okay, so this is the object which is called multi-entropy, and then there's somewhat more generalized version of it. So I think I have to stop here, but this is another application of multi-wave function overlap or multi-inner product or higher inner product. And then that can be used to define various quantities which are useful to investigate topology and then entanglement in quantum many-body systems. So I have 5 more slides to just explain the calculation of this, but part of that is a bit technical, so I think it's okay to stop here. I just wanted to state the general idea of multi-entropy. So let me skip to the summary slide. And I take questions, so maybe it's over already, but thank you for your attention.
Thank you very much.